In machine learning, one decision comes up again and again. Should you fine-tune an existing model or train a new one from scratch? In this video, we'll break this down step by step in a practical way so you can choose the right path based on your data, budget, timeline, and task. Let's start with the big picture. Choosing between fine-tuning and training from scratch is not just a technical detail. It affects how fast you can build, how much money you spend on compute, and how well your model fits the problem. In real projects, this choice can decide whether the solution ships quickly or gets stuck in experimentation. Fine-tuning means taking a model that has already learned from a large general dataset and then adapting it to your specific task. Think of it like altering a ready-made suit instead of stitching one from zero. For example, using BERT for sentiment analysis on product reviews is a classic fine-tuning setup. You keep the strong foundation and customize it for your use case. Training from scratch means you begin with an untrained model. No prior weights, no built-in knowledge. This gives you full control over architecture and learning, but it also demands much more data, time, and hardware. It becomes useful when existing pre-trained models do not match your domain well, like certain medical or satellite imagery problems. Now let us look at this in a simple table format. Fine-tuning vs training. Main practical differences. Here's the core comparison. If your dataset is small, your budget is limited, or you need results quickly, fine-tuning is usually the better option. But if you have a lot of high-quality data and the task is highly unique, training from scratch can be the stronger long-term choice. This table captures the main decision pattern from the article. Data volume is often the first filter. Fine-tuning works beautifully when labeled data is limited because the model already knows useful patterns from earlier training. But if you have a very large and high-quality dataset from your own domain, training from scratch can help capture those specific patterns more deeply. So it's not only about amount but also relevance and quality. Now that we've covered core concepts, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. What does fine-tuning start with? The correct answer is a pre-trained model. Fine-tuning begins with a model that has already been trained on a large dataset and then adapts it to a new task. Question 2. Which approach usually needs more compute resources? The correct answer is training from scratch. Training from scratch requires learning all weights from zero, so it usually takes more time and hardware. Question 3. If you have a small labeled dataset, which option is usually better? The correct answer is fine-tuning. Fine-tuning is especially useful when data is limited because the model already has useful learned features. Now let's talk about task complexity. If your task is close to what a pre-trained model has already seen, fine-tuning can work very well. But if the task is unusual, highly specialized, or structurally different, the transfer may not help enough. In those cases, training from scratch gives you the freedom to build for the exact problem instead of forcing a fit. Let's be practical now. Your GPU budget and deadline matter a lot. Fine-tuning is usually much faster and cheaper. You can often get a strong model in hours or days. Training from scratch may take weeks, especially if you are iterating on architecture and debugging. So if the timeline is tight, fine-tuning is often the safer and smarter choice. The article gives very useful examples. For sentiment analysis with around 10,000 movie reviews, fine-tuning BERT is the natural choice. But for something like high-resolution drone imagery, pre-trained models may not capture the right patterns, so training from scratch can make more sense. The lesson is simple. The method should follow the problem, not the trend. Now that we've covered decision factors, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. Which factor strongly pushes you toward fine-tuning? The correct answer is limited GPU budget. Fine-tuning is more compute efficient, so it is usually preferred when hardware budget is limited. Question 2. When is training from scratch more justified? The correct answer is when the task is highly unique. A highly unique task may not align well with existing pre-trained models, making scratch training more suitable. Question 3. Which example from the article fits fine-tuning best? The correct answer is movie review sentiment analysis. The article specifically mentions fine-tuning BERT for sentiment analysis as a strong practical example. One of the most practical insights in the article is this: training from scratch may improve performance slightly, but the gain is not always worth the extra cost. In many business cases, getting nearly the same result much faster through fine-tuning is the better trade-off. So don't judge performance only by accuracy. Also consider training time, cost, and deployment speed. The article also points to some advanced techniques. You can first pre-train on domain-specific text and then fine-tune, which can improve results in areas like finance. Multitask fine-tuning lets one model learn related tasks together. And parameter-efficient methods like LoRa are very useful for large language models because they reduce how many parameters need updating while still giving strong adaptation. A strong case study from the article is healthcare image classification. With only around 10,000 X-ray images, fine-tuning a pre-trained ResNet 50 delivered excellent accuracy in less than a day on a single GPU. That's a great reminder that there is no universal winner here. The best approach depends on your data, domain, and constraints. Now that we've covered practical takeaway, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Why is fine-tuning often preferred in business settings? The correct answer is, it gives the strong results faster. Fine-tuning often reaches near-scratch performance in much less time, which is valuable in real projects. Question 2. What is LoRa mainly useful for? The correct answer is updating fewer parameters efficiently. LoRa is a parameter-efficient tuning method, especially useful for large models. Question 3. In the healthcare case study, why was fine-tuning a good fit? The correct answer is, the dataset was very small. With limited labeled medical images, transfer learning through fine-tuning was more practical than training from scratch. If this helped you understand the trade-off clearly, you now have a practical framework for making the choice in real machine learning projects. The best model strategy is not the fanciest one, but the one that fits your constraints and goals.